All right, so here we've got the notes for section 8.1, which deals with accumulation and net change. So linear motion, example 1, the velocity of a particle moving along a horizontal s-axis from 0 to 5 is given by this equation. So ds dt is the same thing as velocity, t squared minus 8 over t plus 1 squared. Describe the motion. So if we look at the graph of this guy, we're going to graph it in terms of x because the variable doesn't actually matter. We get something that looks like that. Now, I'm only concerned with the positive part because it says from 0 to 5. So if we scroll down, we can see it starts with, so we know that V0 is -8, because that's where it crosses there. And then so it's moving left, just a negative velocity. And then at, looks like about, say 1 1/4 seconds, it pauses. And reverses direction, because that's now where the velocity is now positive. So there you go. Okay, so example 2, suppose the initial position of the particle in example 1 is at 9. What's the particle's position at t equals 1? At t equals 5. So what we can do is we can do the antiderivative, because the antiderivative velocity is position. So from 0 to 1, t squared minus 8 over t plus 1 squared dt. So menu, and we'll see my calculator handle this. I don't want to work this guy out. X squared minus 8 over quantity x plus 1 squared from 0 to 1. So we get -11/3. So that means it travels -11/3 in the first second. So if it starts at 9, we do 9 minus 11/3. And we get now sitting at the position 16/3. So you can do the same thing down here at 5 seconds. So from 0 to 5 of our equation. If we run that in the calculator, we find this displaced 35 units to the right. So if it starts at 9, moves 35 units to the right, it's now at 44. So the displacement of an object is given by the integral of its velocity. To find the total distance traveled is a little bit different. To find the total distance, we take the absolute value of our velocity, because we're going to assume that it's always moving in the positive direction. So we're working this equation. So you can also break it. You could do the negative integral from 0 to 1.25, because that's where the velocity was negative. And then plus from 1.25 up to 5 of our equation, if you wanted to break it into 2 parts and don't have to worry about the absolute values. But as we have a calculator, absolute value is not really that big of a deal. So, and if we let our calculator handle this, this comes about to be 42.89. So it's traveled total 42.89 units, or 59. Okay, so general strategy here. Modeling with integrals, approximate what you want to find as a Riemann sum of values, continuous function multiplied by interval lengths. If f of x is the function, a, b is the interval, you partition the subintervals of length delta x. Approximating sums will have the form, so this is the height, and that's the width, so that's your area of the rectangle, with c of k some point in each interval. So we write a definite integral, which is easy to calculate. And as the norms, the partitions go to 0, so we're making our rectangles narrower and narrower. Evaluate the new integral numerically or with the antiderivative. So numerically means with the calculator. Antiderivative is the algebra method. Okay. Car moving with initial velocity of 5 accelerates at the rate of this. miles per hour per second for 8 seconds. How fast is the car going when the 8 seconds are up? So let's see here. So velocity is the antiderivative. So we can figure out how much the velocity changes in the first 8 seconds if we work this out. This would be 1.2 t squared from 0 to 8, which comes out to be 76.8 miles per hour. So the change in velocity is that much. It's already going 5. So at the end of the 8 seconds, it's going 81.8 miles per hour. So to do this, I need the velocity equation. Well, the antiderivative acceleration gives me velocity, but since I'm already traveling 5, my velocity equation is 5 plus 1.2 t squared. So how far did the car travel? So that would be 0 to 8. We do the antiderivative of our velocity. Now, I technically would need opposite value bars here, but since this is always positive anyway, it doesn't actually matter. There's no way for this number to come out to be negative. So the antiderivative of 5 plus 1.2 x squared from 0 to 8 comes out to be 244.8. Now, the issue is this is mile per hours per second, or miles per hour second, because 8 seconds, our speeds are in miles per hour. So let's see here. We would need to multiply this by 1 over 3600 to make it a more useful unit, to get it into something, because hours is 60 minutes, which is 60 seconds, or 3600 seconds, so that'll actually cancel our seconds out. Oops, not times. So this comes out to be 0.068 miles, which is about times 5280, 359 feet. And now if you actually want to work the antiderivative out, this would become 5t plus 0.4t cubed. Count up the exponent, reciprocal comes out front, from 0 to 8. But you would still get the same answer at the end. Okay, consumption over time. Example 5, from 1970 to 1980, the rate of potato consumption in a particular country is modeled by this equation, with T being years since the beginning of 1970. How many bushels were consumed from the beginning of 72 to the end of 73? So the beginning of 72 is 2 years after the beginning of 1970. The end of 1973 is 4 years. All of 72, all of 73. So that's 4 years later. And then we do our equation. And then we're going to let our calculator handle this. So the antiderivative of 2.2 plus 1.1 to the x from 2 to 4. So equals 7.07. That's in millions of bushels. So that's the total consumption. All right. So example 6. From noon until 6 p.m., the rate at which people enter amusement park at the time t is given by E of t, which the graph is over here, where t0 corresponds to noon, and 6 is 6 p.m. People are also leaving, so entering for E, leaving. If 3,000 people are in the park at noon, how many people are in the park by 6 p.m., rounded to the nearest multiple? So if this is the rate people enter, the area is the total number of people who have entered per unit time. If you look, I've actually got 3 figures here. I have this trapezoid, I have a rectangle, I have another trapezoid. So our equation to set up here is we start with 3,000 people plus people in, which is the area up here, minus people out, which is that equation. So people in the area here, let's see, to find the area of a trapezoid, it's 1/2 the average of the bases times the height. so sorry, 1/2 base plus height. So this is 400, that's 600. So people in is going to be 1/2. The height here is 1, 2, 3. Usually it's tipped on its side. And then it's 400 plus 600. So that's that part. Plus the area here. So that's just a rectangle, 1 unit wide by 1, 2, 3, 4 by 600 units tall. And plus the other rectangle trapezoid over here. So that is 2 hours. And the two bases are 600 and 500. Now people out, from 0 to 6, since I have the goofy equation, I have to work out the integral. 500, 2 plus t squared e to the negative t over 5. So all in, we've got 3,000 people to start. 0.5 times 3 times 1,000 plus 600 plus 0.5 times 2 times 1,100. So a total of 3,200 people come into the park. Leaving the park, x squared e to the negative x over 5 from 0 to 6. We have about 2,100 people, it looks like. All right, so we need a total, we have a 2,106 if we work out the integral. So starting people, people in, people out. So this is 3,000 plus 3,200 minus 2,106 gives us 4,094. To the nearest multiple of 100 though, that would be there are 4,100 people in the park at 6 p.m. Okay, for example 7, sometimes you are not able to not have a nice equation, and it might be tedious to draw the shape. This case, since we have values, we can actually use what's called a trapezoid rule from previous. So the trapezoid rule gives us, our range is 60 here. There are 12 subdivisions. And then what we do is we take each number plus, and then all of the other values are doubled until you get to the last one, which is just 63. So only the first and last one will appear once because they only form one edge of the shape. All the other shapes, so the 60 is the right edge of the first shape, but the left edge of the second. If you work this all out, you get 3.8, or whoops, not 3.8, 3.5, 82.5 gallons total pumped, if this is our rate and that's the time. So what we're doing is we're making a bunch of trapezoids. So with 5-minute increments across the bottom, and the heights change. So, and this is adding them all up. Alrighty, density. 10-mile stretch of rural Minnesota road is bounded to the north by colonies of pockets. So this distance is 10 miles. So there's our road. There are gophers. 50 per, or along the road, the density is 50 per square mile. It increases linearly until it reaches 2,003 per square mile, 3 miles from the road. So our population equation is 500 plus 500, we'll just call it x, where x is the distance you are from the road. Find the total population of gophers in this stretch of land that is 10 miles long and 3 miles wide. So let's see here. So since it's 10 miles wide, we need to multiply this by 10. So starting at the road, going 3 miles away. So it's going to be 5,000 plus 5,000x dx. So calculator says 5,000 plus 5,000x from 0 to 3 gives us 37500 gophers. If you do want to antiderivative this would become 5,000x plus 2,500 x squared from 0 to 3. So count up the exponent, so on and so forth. All right, example 9. Takes a force 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching it 4 from its natural length? So this uses Hooke's law here. So Hooke's law is given by F equals kx. So it takes a force of 10 newtons to stretch a spring. So we're going to have to solve for k. So the spring constant is 5. So from 0 to 4 of our force function gives us work. So work is the antiderivative of the force. So here's your force equation from 0 to 4. So this become 2.5x squared, evaluated from 0 to 4. So 2.5 times 4 squared minus 2.5 times 0 squared. So this is 2.5 times 16 minus 0. So 2.5 times 16 is 40 Newton meters. And that is the end of the section.